Morning. My name is Manikesh Kumar Jha. I am working as an assistant professor in Electronics and Communication Engineering Department at IIMT College of Engineering, Greater Noida. So today we are going to discuss about the topic basic of Laplace transform. So there is a wide range of Laplace transform is there and their applications. So main applications of Laplace transform to solving the differential equations. In mathematics, when we are solving the differential equations, there we are using the Laplace transform. The application of Laplace transform also used in the network theory. So when we are solving the networks theorems or network theory questions, in that questions we are applying the Laplace transform. Similar as in control system domain, when we are solving the state space analysis, in that state space we are also applying the Laplace transform. So there are the large area where the Laplace transform applications are used. So today we will see what is Laplace transform, what are the properties of the Laplace transform, how we find the inverse Laplace transform, and what is this Laplace transform. So today we will discuss about this. So the next one, first we are going to discuss about what is Laplace transform. So the Laplace transform is an integral transformation of a function f of t from the time domain into the complex frequency domain given as f of s. So basically, the Laplace transform is nothing but the transformation from time domain to the complex frequency domain. So time domain function, when we are defining the functions in time domain, we are represented as f of t. So this is function of time. Similarly, when we are going to define it is the function in complex frequency domain, we are represented as f of s. So s is nothing but the complex frequency. So S is the complex frequency, which is given as sigma plus j omega, where sigma is the attenuation factors and omega is your angular frequency. So basically, Laplace transform is the transform from the time domain to the complex frequency domain. So here when we see that this is the L of ft, means this is Laplace of function f of t in time domain. Then when we are taking the Laplace transform in domain at time domain, so in complex frequency domain, the Laplace transform of ft is given as f of s. So this is the Laplace domain f of s. So it is represented how we find it. So we can find it by integration. So what is the formula? So integration from 0 to infinity function in time domain, that is f of t e to the power minus st dt. So this is the formula to finding the Laplace transform in the time domain. Here already I discussed that S is the complex frequency. Here we see the integration. We are going to integrate it from the 0 to infinity. So this is known as one-sided or unilateral. So this is, we are going to taking only the positive side of time. So this is the unilateral or one-sided Laplace transform. If we are taking the integration from minus infinite to plus infinite, so we are going to integrate within the time from minus infinite to plus infinite, means we are taking the negative value of time as well as taking the positive value of time. So we are taking the range of time from minus infinite to plus infinite. Then it is known as bilateral Laplace transform or two-sided Laplace transform. So now we are going to take some examples. So in the first example, we are saying that the first signal is u of t. This is the unit step signal. The next one signal we are going to take is e to the power minus at ut. This is the decaying exponential. So this is the decaying exponential signal. And third one we are going to take is as del of t. That is the impulse signal. So three signals we are going to take. Now we will discuss about what will be the Laplace transform for this signal. So one by one we will discuss how we find the Laplace transform and what will be the Laplace transform for this unit step signals, decaying exponential signals, as well as the impulse signal. So first we are going to take it the u of t, the unit step signals. So as we already know that when we are going to discuss about the unit step signals, so unit step signals is defined as when t is greater than equals to 0, the value of ut is 1. When t is less than 0, the value of ut is 0, as we already know. So when we are going to take is the Laplace transform, so Laplace transform of ut is f of s. So this is a complex frequency domain. So this is represented as f of s. How we find it? Integration 0 to infinity. When we are taking the time from 0 to infinity, so we know when time is positive from 0 to infinity, the value of ut is 1. So we are taking 1 into e to the power minus st dt. So when we are going to integrate these signals, we are getting 1 upon s. So the Laplace transform of unit step signal, we are getting 1 upon s. Similarly, the next function we are going to take as the decaying exponential signal. So when we are taking the decaying exponential, so what is the decaying exponential? E to the power minus at into u of t. So this signal is also multiplied with u of t. When any signal is multiplied with unit step signals, it means that signal will be defined only for the positive time. Means it will define from 0 to infinity. Then what will be the effect, sir, if we are taking the negative time? Then for the negative time, minus infinite to 0, it is getting 0. Because for the negative time, unit step signal can't define and it will give you the value as 0. So when we are taking the Laplace transform f of s, so it is getting 0 to infinity e to the power minus at, and this is the Laplace domain. When we are finding the Laplace transform, so it is multiplied with e to the power minus st into dt. So when we are going to integrate it, as we know that when we are going to multiply the two functions or two signals, the power getting added. So how much we are getting? E to the power minus s plus a into t dt. When we are going to integrate from 0 to infinity, we are getting 1 upon s plus a. So from this we understand the Laplace transform of e to the power minus at ut is 1 upon s plus a. This a is same as this a. So this A and this A both are the same. So next one is your ramp impulse signal. So when we are going to take the impulse signal, so impulse signal we know that impulse signal is defined as at t equals to 0 only. So when we are taking time t equals to 0, impulse signal has some value. So it will define at t equals to 0. If we are taking the other value means other value of time rather than 0. We are taking any value other than 0. It means 0 0.1, 0 0.2, 1, 2, 3, 4, any value. The value of the impulse signal is 0. So this is the impulse signal property, or we are defining the impulse signal in this manner. So when we are going to take the Laplace transform, so this is f of s. So f of s, how much we are getting? Integration 0 to infinity del of t, that is the impulse signal, e to the power minus st dt. As I already tell you that impulse signal defined only at t equals to 0. So it is only defined at t equals to 0. So it means e to the power minus st at t equals to 0. When we are putting t equals to 0, so e to the power minus 0 is how much we are getting? 1. So we know anything to the power 0, we are getting 1. So the impulse signal, when we are taking the impulse function, the Laplace transform of the impulse function is 1. So these are the three basic signals in which we are going to discuss about the unit step signal, unit impulse signal, and the decaying exponential signal. And we will see, we saw the Laplace transform of these three functions. So when we are discussing about the unit step signal, Laplace transform of 1 by s. When the decaying signal, exponential signal, that is 1 upon s plus a Laplace transform. And when we are discussing about the impulse signal, the Laplace transform is 1. So there are some basic signals. Here are some basic signals, that is impulse signal, step signal, ramp signal, exponential signal, sine signal, and cosine signal. These are the basic signals. So these basic signals, we have to remember the Laplace transform of these basic signals. Why we have to remember? We have to remember because when we are solving the Laplace transform questions, so in between the questions, this function came. In between intermediate step, these functions are came in between the questions. So when we remember the Laplace transform, so directly we are applying the Laplace transform of that function. No need to evaluate or equate the what is that Laplace transform of ut or del t or rt or anything. So basic signals we remember, we just apply the Laplace transform. So these are the basic signals. The first one is impulse signal. So impulse signal represent as del of t, and we see that what is the Laplace transform, that is 1. Next one is the unit step signal. It is represented as u of t, and we see the Laplace transform as 1 upon s. Similar, the next one is unit ramp signal. So unit ramp signal is represented as r of t, and r of t is nothing but the t u of t. So ramp signal is similar as triangular signal. So this is represented as t u of t. So the Laplace transform of the ramp signal is 1 upon s squared. Similarly, when we are discussing exponential signal, so e to the power minus st, at, that is the decaying exponential. And we will see that what will be the Laplace transform? 1 upon s plus a. Similarly, sine and cosine signals are there, sine omega t and cos omega t. The Laplace transform for sine omega t is omega upon s squared plus omega squared. Similarly, for cos omega t is s upon s square plus omega s. So these are the basic signals and their Laplace transform. So we have to remember it. So the next signal is damped ramp signal. Damped signal, we understand that e to the power minus at. It is still talking about ramp signal. So t e to the power minus at. So when we are finding the Laplace transform, here we are applying the property of the Laplace transform. So here what will be the property? It is multiply by t. So here we are applying the property as differentiation in the S domain property. When we are applying that property, we are getting the Laplace transform as 1 upon s plus a whole square. Similarly, damped sine. So e to the power minus at denote the damped, and this is sine signal. So sine omega t. So when we are finding the Laplace transform, it is getting omega upon s plus a whole square plus omega square. Similarly, damped cosine. So e to the power minus 60 at cos omega t. When we are finding the Laplace, so it is getting s plus a upon s plus a whole square plus omega square. So next one we will see. Next one, the basic signals. And what is the basic signals? We already discussed that first signal is step function, unit step function. So the symbol for the unit step function is KUT. It is defined as KUT. So UT is your unit step function. I am telling you that for the unit step signal, how it is defined? For t greater than equals to 0, it is 1. For t less than 0, it is 0. But it is what where it is KUT. So say it is multiplied by K. So when t is greater than 0, ut is 1 and 1 is multiplied with k. So we are getting k. When t is less than 0, what is the value of ut? 0. So 0 into k, we are getting 0. So KUT is defined for t greater than 0. This is k. For t less than 0, this is 0. So this is the graphical representation of KUT. So I already tell you when t is less than 0, the ut is 0. So 0 into k, this is 0. When t greater than 0, the ut value is 1 and 1 into k is k. So from 0 time t 0 to infinity, the value of KUT is k. Similar step functions. So what we are going to do when we are seeing these functions, this graphical representation. So for before time t equals to 0, what is the value? This is 0. After at t equals to 0, when we see at t equals to 0, so it is getting 0. At t equals to 0, there is one jump from 0 to k. There is a jump from 0 to k. So at t equals to 0, one discontinuity is there. So we will see here one discontinuity is there. So what I am going to tell you that discontinuity of the step function may occur at some time other than t equals to 0. So here we are taking that u of t signal. So discontinuity occur at t equals to 0. He is telling that this discontinuity will be occur at some different time instant. Yeah, definitely it will happen. How? When we are applying the shifting properties. When we are applying the shifting properties on the signal, then the discontinuity time instant will be different. As we see that we are taking the signal KU t minus a. KU t minus a. It means the initial signal KUT. Now we are writing KU t minus a. So we are shifting the KUT signal by a unit. This is minus a. So we are going to delay the signal. We are delaying signal means we are going to right shift the signal. So it means we are going to shift the signal by a unit. In which direction? In which right direction. In right shift. So when we are going to define it, what is the time instant? The time instant is now compared with a. So t is greater than a, it is k. When t is less than a, it is 0. So when we are defining the graphical representation, so we will see the graphical representation as what is the time instant? Now the time instant is a. So before a, the value of KUT minus a is 0. After a, what will be the value? After a, it is getting k. So from a to infinity, when time from a to infinity, the value of KUT minus a is k. So this is the graphical representation. So this is the graphical representation. So next, what we are going to take, we are going to take some triangular signals. Here is some triangular signals is there. So what is the time instant? Time instant is 0, 1, 2, 3 and 4. So we will see from 0 to 1. From 0 to 1, one line is there. Okay, from 0 to 1, one line is there. From 1 to 3, one line is there. Also, from 1 to 3, one line is there. Again, from 3 to 4, one line is there. So there are 3 line equations will be there. With first line equation between 0 to 1, second line equation from 1 to 3, and third line equation from 3 to 4. So we will get 3 line equations. So 3 linear equations at t equals to 0, t equals to 1, t equals to 3 and t equals to 4. This is the time instant where slope getting changes and we are getting the line equation. So here we will see from 0 to 1. When we are taking from 0 to 1 this line, what is the line equations? Line equations is 2t. How we find the line equations? So straight line equation we understand that y equals to mx plus c. That is the line equations of the straight line. What is m? M is the slope. How we find the slope? So slope we are going to find is y2 minus y1 upon x2 minus x. So this is the formula to finding the slope. So from that we are getting from this line 0 to 1. How much the line equation is 2t. Similarly from 1 to 3. From 1 to 3 this line. What is the line equations? We are getting minus 2t plus 4. Similar from 3 to 4. When we are getting 3 to 4 line, we are getting the line equation as 2t minus 8. So 3 line equation we are getting. What next what we are going to do? So linear functions, 3 linear functions are there. First line equation 2t, second one is minus 2t plus 4, third one is 2t minus 8. So the first line is starting from 0 and the slope change at t equals to 1. So at t equals to 0 it is getting on. So we will see that the 2t signal, 2t line is on at t equals to 0 and off at t equals to 1. Similarly second line is from 1 to 3. So it is on at t equals to 1 and off at t equals to 3. Third line is starting from 3 to 4. So runs between 3 to 4. So it is on at t equals to 3 and off as t equals to 4. So this is the line equations and where it is getting on and off we will see there. So a step function can be used to turn on and turn off this function. The step function can be used as turn on and turn off as a switch we can use. So when we are defining that rectangular signal, that triangular signal is there. So when we are defining that triangular signal in unit step function, if somebody tell me that triangular signal is given and you have to define that triangular signal in the form of unit step signals. So how we find? So first line equation is 2t and that is between 0 and 1. So time instant is 0 and second time instant is 1. So first time instant is 0. So we are writing ut minus second time instant is 1. So u of t minus 1. Similarly plus second line equation is minus 2t plus 4. So it is between 1 and 3. So u of t minus 1 minus u of t minus 3. Similar third line equation is 2t minus 8 and it is between 3 and 4. So 2t minus 8 u of t minus 3 minus u of t minus 4. So that triangular signal can be represented in the form of unit step signals. So this is the representation of triangular in the form of unit step signal. So next one, impulse function. So impulse function, what I am going to tell you, the impulse function symbol is del of t. This del of t is representation of the impulse function. So mathematical, what is the property of impulse function? So first property is this one, minus infinite to infinite del t dt equals to 1. So this property is known as the area property of impulse. So when we are going to integrate from of any signal, when we are going to integrate any signal from minus infinite to infinite, it means we are going to find the area of that function. So this is, we are going to find the area of the impulse signals and the area of the impulse signals is 1. So it is also known as the area property of the impulse function. Second, we are already tell you that impulse function is only defined at t equals to 0. If we are taking any value except t equals to 0, the value of impulse is 0. So it is given as del t equals to 0 if t is not equals to 0. So this is two property of the impulse function. So the area under the impulse function is constant. So we will see that what is the impulse function? The area of impulse is 1. That is the constant. So area under impulse function is constant. And this represents the strength of the impulse. And it will show you that what is the strength of that impulse. So impulse is 0 everywhere except t equals to 0. So I already tell you that impulse is only defined at t equals to 0. So any impulse that occur at t equals to a, if some impulse, I am going to tell you that one impulse signal is there, or what is the time instant? That is the time instant is t equals to a. Then it is defined as k del t minus a. We are going to shift that del t signal by a unit, and new time instant getting t equals to a. So when graphical, we are going to see that this is defined at t equals to 0. So this is k del t. it is defined at t equals to a at time instant a, it is going to define. So it is written as k del t minus a. It is going to the del t signal is shifted by a. So this is k del t minus a. This is the graphical representation of the impulse signal. So some properties of the impulse Laplace transform are there. So some properties, the first property we are going to discuss about the linearity property. What is the linearity property? So linearity property we are going to define in the manner if we are taking two signals f1t and f2t. So f1t signal, the Laplace transform of f1t is f1s and f2t Laplace transform is f2s. So when we are f1t and f2t signals are there, Laplace transform is f1s and f2s. When we are taking the Laplace transform of a1 f1t plus a2 f2t, then the Laplace transform is given as a1 into f1s plus a2 into f2s. So this is the linearity property. And the linearity property defined by how we tell that this is linear function or linear system. So for the linear system, two things are verified. The first one, homogeneity principle, and second one is the superposition principle. So if two is verified, then we tell that the system is linear system. So this is the linearity property of the Laplace transform. The next one is the scaling property. So once the signal we are going to take as f of t, Laplace transform is f of s. Now we are going to scale that f of t signal by a. So this a is the scaling factor. So new signal what we are going to take f of at. Now we are going to take the Laplace transform of f of at. So it is given as 1 upon a f of s by a. So this is the scaling property of the Laplace transform. Similarly, third one is the time shift in the time domain. Time domain shifting property. So shifting property when we are going to tell, then Laplace transform of ft is f of s. Now we are going to shift this time t by a unit. So now we are going to take the signal as f of t minus a, u of t minus a. So we are going to shift the signal by a unit. So the Laplace transform is e to the power minus as into fs. This a is same as the shifting unit. How much shift we are going to provide? This a and this a, both are same. So the shifting property when we are going to see, so it is getting e to the power minus as into f of s. So next one, inverse Laplace transform. So inverse Laplace transform, what is inverse Laplace transform? So first of all, we have to discuss Laplace transform. So Laplace transform, we see that this is the transform from time domain to the complex frequency domain. That is the S domain. So when we are taking the inverse Laplace transform, so it is the transform from complex frequency domain, that is our S domain, to the time domain. So it is f of s is given as ns upon ds. Ns is the numerator polynomial and ds is the denominator polynomial. So any function is defined as numerator by denominator polynomials. So the main functions, then we are discussing about the inverse Laplace transform. The main method of the inverse Laplace solving the inverse Laplace transform is partial fraction method. So we are using partial fraction method. We are finding the inverse Laplace transform. So some examples we are going to take. The first example we are going to take that f of s equals to 3 by s minus 5 upon s plus a plus 6 upon s squared plus 4. So when we see this signal, first term 3 by s, so 1 by s is there. So when we are taking the inverse Laplace transform, so we already know that the Laplace transform of ut is 1 by s. So what will be the inverse Laplace transform of 1 by s? It will give you the ut. So first signal, this is nothing but your 3 ut, 3 into u of t. Second signal, 5 upon s plus a. So we already saw that 1 upon s plus a, whose Laplace transform is 1 upon s plus a, that is e to the power minus at ut. When we are discussing about the Laplace transform e to the power minus at ut, we will see the Laplace transform is 1 upon s plus a. So here it is 1 upon s plus 1. So what is the value of a? A value is 1. So we are getting 5 e to the power minus t ut. So for the second function, inverse Laplace is 5 e to the power minus t ut. Third one is 6 upon s squared plus 4. So whose Laplace transform is? We will see the Laplace transform of sine and cosine. So for both, the denominator is s squared plus omega squared. And numerator is omega upon s squared plus omega squared. It is comparable with omega upon s squared plus omega squared. So this is the inverse Laplace of sine function. And this is omega. What is the omega? Omega is 2 because in denominator we are writing s squared plus omega squared. So omega squared is 4. So omega is 2. So it is nothing but sine of 2t. Sine of 2t. So when we are taking the inverse Laplace, so it is given as 3 ut minus 5 e to the power minus t ut plus 3 sine 2t ut. So for all the three signals, ut is common, so we are taking it outside. So 3 minus 5 e to the power minus t plus 3 sine 2t into ut. So this is the inverse Laplace transform. The next question, when we are going to, I'm telling already tell you that the main functions when we are solving the inverse Laplace transform, the main method is the partial fraction method. So one question is there, f of s is 96 into s plus 5 s plus 12 divided by s plus 8 s plus 6. So one f of s is there. So now we are going to find the inverse Laplace transform. So what we are going to do? We are solving using partial fraction method. So when we are solving using partial fraction method, so in that we have to find first number of poles. Where is the pole location? For this signal, where is the pole? So we already know that pole. What is pole? Pole is the roots of the denominator. So denominator part is this one, s into s plus a, s plus 6. This is the denominator part. So what is the root? S equal to 0, s equal to minus 8, s equal to minus 6. So we are getting S1 is 0, S2 is minus 8, S3 is minus 6. So three pole we are getting. So what? So all three poles are distinct. So what we are going to write is as, so we are going to write it as 96 into s plus 4, s plus 12, s into s plus 8, s plus 6 can be written as k1 upon s, k2 upon s plus 8, and k3 upon s plus 6. So what is now what we are going to tell it? So if we are going to split it into three polynomials, k1 upon s, k2 upon s plus 8, and k3 upon s plus 6. So here we are going to find k1, k2, and k3. So what we are going to do is, now we are going to find the value of k1, k2, and k3. So what is the denominator of k1? S. So where is the pole location? S equal to 0. So for finding k1, we are going to find that s equal to 0. Similarly, for K2, what is the denominator? S plus 8. So K2 will be defined at where? S equal to minus 8. Similarly, K3 will be defined at where? S equal to minus 6. So 3 points, 3 poles we are getting 0, minus 8, minus 6. So at 3 points we are going to define and finding K1, K2 and K3. How we find it? So for finding K1, this is the polynomial is given 96 s plus 5 s plus 12 and this one at s equal to 0. So K1 plus K2 s upon s plus 8 at s equal to 0 plus K3 s upon s plus 6 at s equal to 0. When we are putting s equal to 0, so for when we are putting s equal to 0, so second term and third term, K2 and K3, it is getting cancelled out because it is getting 0. So from here we are getting K1. So K1 how much we are getting? From in this expression we are putting s equal to 0. So how much we are getting? 96 into 5 into 12 divided by 8 into 6. After solving, how much we are getting? 120. So K1 we are getting 120. Similarly for K2, where it is defined, it will define at s equal to minus 8. So this is the expression at s equal to minus 8. K1 into s plus 8 upon s plus 6 at s equal to minus 8 plus K2 plus K3 expression is here K3 into s plus 8 s into s plus 6. Where it is going to define at s equal to minus 8. When we are putting s equal to minus 8, so this first term K1 expression, K1 getting 0 and similarly K3 getting 0. So minus 8 when we are going to put, so numerator getting 0, so these both are cancelled out. So from here we are getting K2. K2 value how much we are getting? 96 into this one expression. We are putting s equal to minus 8. So we are getting 96 into minus 8 plus 5 is minus 3. Minus 8 plus 12 is 4. Divided by numerator minus 8 into minus 8 plus 6 is minus 2. So after solving we are getting minus 72. So K2 we are getting minus 72. Similarly for K3, so K3 will be defined as equal to minus 6. So in expression we are going to find, we are going to put the value of s equals to minus 6. So this K1, K2 cancel out. From here K3 we are getting how much? So 96 at 96 into minus 6 plus 5, it is getting minus 1 and s plus 12, s value is minus 6. So it is getting 6 divided by minus 6 into 2. So K3 we are value we are getting 48. So K1, K2, K3 we got. So f of s is 1 by 120 by s minus 72 by s plus 8 plus 48 upon s plus 6. So when we are going to see it, so this is 1 by s. So inverse Laplace transform is ut. Here 1 upon s plus 8. So it will be function of e to the power minus 80 ut. Similarly, third function 1 upon s plus a e to the power minus 80 ut. So when we are taking the inverse Laplace, f of t is given as 120 u of t minus 72 e to the power minus 80. What is the value of a? This one. So e to the power minus 80 ut plus 48 e to the power minus 80. What is the value of a? 6. So e to the power minus 60 ut. So ut is common in all the three expressions. So we are taking ut as common from all the three expressions. So we are getting the inverse Laplace as 120 minus 72 e to the power minus 80, 48, 6 e to the power minus 60 ut. So this is your inverse Laplace. So in this session, we know how to find the Laplace transform. What is the Laplace transform for the basic signals? What are the property of the Laplace transform? And how we find the inverse Laplace transform. So this is all about this session. Thank you.